In this module, we're going to lay some basic definitions, some foundations for some of the work that we're going to be doing the rest of the semester. We're going to be learning some technical definitions for terms that we are used to using in our everyday lives, such as work, energy, power, force, acceleration. But we have to know the technical definitions in order to understand what's going on when we're later going to be talking about things like how does a windmill work, or how do I get energy from water going through a dam. So we're going to learn those technical definitions, and then over the course of the module, we're going to learn how they interact with each other and how to do some simple quantitative problem solving with those. We're going to start off with Newton's laws of motion, Newton's three laws of motion. And in some sense, Newton's laws all say the same thing. But it's helpful to have the three of them broken down because it's sort of three different ways of looking at things. Newton's first law of motion seems very simple, but it's actually counterintuitive based on our everyday experience, and I'll explain why that is, and there are some demos that will illustrate this as well. Newton's first law of motion says an object will continue moving at a constant velocity unless acted upon by a net force. And I've highlighted both velocity and force here because those are both terms that we're calling vectors, or quantities that are called vectors. And a vector has both a magnitude, and that basically means a size, and a direction. So a quantity such as, say, temperature does not have a direction. It's not 35 degrees that way or 72 degrees this way. It's just a magnitude. It's just a number. So temperature is not a vector. Velocity is your speed in a particular direction. So it's a vector. If I say I'm going down the highway at 70 miles per hour, that's not enough information to call it a velocity. That's only my speed. That's only the magnitude of my velocity. But if I say I'm going 70 miles per hour due east, then those two pieces of information together are the velocity, and that's a vector. And a force is also a vector. The magnitude of force is measured in a unit named after Isaac Newton called the Newton. And basically, Newton's first law defines what a force is. It is a push or a pull that causes an object's velocity to change. Now notice it's very important to say the velocity and not the speed, because I can change the velocity of an object without changing its speed. If I have an initial velocity this way, I write v with a little arrow over it, and maybe it's traveling at 30 miles per hour in this direction, and that's my initial velocity. I could have some later velocity this way that's also 30 miles per hour. That's my final velocity. And notice the speed is the same, but here v initial is not equal to v final because the directions of those two arrows are different. So something had to happen to change the direction of the thing going from this way to going this way, even though the speed didn't change at all. So if you're driving your car down the highway and you get off on the exit ramp, even if you keep your speed the same, the fact that you're changing a direction means there must be some force acting on you. So force is a push or a pull on an object that causes the object's velocity to change. Newton's second law of motion basically quantifies the first law. The second law says that the net force acting on an object is equal to the mass of that object times the acceleration of that object. So the equation written out here in vector form, F equals ma, and on the notes here I've written the F and the A with arrows over them to indicate that they are vectors. So acceleration now is another term we're familiar with in our everyday life that is technically a vector. It has a magnitude and a direction, and the acceleration is the rate of change of velocity. So This, you can see, is saying the same thing that Newton's first law says, which is that a force is required to change the velocity, and Newton's second law says, well, the force is equal to the mass times the acceleration, and the acceleration is a measure of the change in the velocity. Why are these a little bit counterintuitive? Well, in our everyday experience, things tend to come to a stop. And that's because in our everyday experience, we always have a force acting on things that we sort of take for granted and we don't really think about. And that force is friction. But in the absence of that force, if something is moving along at some speed, it's going to continue moving along at that speed and in that same direction for all time, for all eternity. Something has to come along and do something to it in order to make it slow down or change its direction. And finally, Newton's third law of motion, and we'll have some demos to illustrate that, is that I'm sure familiar with this phrase, for every force there is always an equal and opposite reaction force. And that means that in order to change the velocity of an object so that it moves in a different way, something else has to exert a force on it. Well, if I'm exerting a force on something else to change that thing's velocity, that thing must exert a force back on me. And the universe would be a very strange place if we think about it, if Newton's third law did not describe the universe. So, for example, if things could just spontaneously change their state of motion without any consequences happening in the other direction, then things could just spontaneously move around and slide around without anything causing that to happen. Uh, Another way of thinking about Newton's third law is in the concept of a system, which we'll talk a lot about in the context of energy and conservation of energy. And that is an object such as my pen here. If I define this object to be a system, in order for it to change its state of motion, and right now its velocity is 0, in order for it to change its state of motion, there must be a force acting on it. So if I let go of it, it moves, and that means its velocity went from 0 to a non-zero number. I can't seem to balance it, so it lands exactly on my hand here. But what is the force that is acting on it to make it move? It's the force of gravity, and the object that is exerting that force of gravity is the Earth. If we do another example and I just push the pencil like that, or pull it like that, I've changed its state of motion by exerting a force on it, and it's pulling on me in the opposite sense. You can do a demonstration at home to convince yourself of Newton's third law, and that is to test out the old expression of, can you pull yourself up by your bootstraps? So after this video is over, or even right now if you want, stand up, bend over, grab your ankles, and pull up with all your might. And no matter how strong you are, and no matter how hard you pull, you will never be able to pick yourself up off the ground. That's even if you're a strong enough person where you can lift the weight of yourself. Why is that? Because your hands might be pulling up on your ankles with enough force to lift them off the ground, but your ankles are pulling down on your hands with an equal and opposite force. And since they're all connected as part of one body, you don't go anywhere. So Newton's laws all basically say that a force and only a force can cause a change in an object's velocity, and we describe that change in velocity with a quantity we call acceleration. So test yourself with these questions, see how you do, and let me know online if you've got any follow-up questions on Newton's laws.